Welcome to today's Geofabrics Academy session titled Determining the Allowable Design Strength of Geosynthetic Reinforcement. My name is Gordon Stevens. I'm the Technical Manager for Geofabrics in New Zealand. I've been in the industry, geosynthetic industry, for getting on 30 years now, and I've seen quite a lot of geosynthetic reinforced soil structures over this time. I've been involved in looking at design and the construction side. I've seen it through the eyes of the designer, through to the eyes of the contractor. And there's a lot of uncertainty when it comes to the determining of the allowable design strength of geosynthetic reinforcement. And this session today is designed to try and address some of that uncertainty. If you could put any of your questions in the Q&A section, and the recording of this webinar will be made available in the Academy after the webinar later today. So let's start with a simple question that designers encounter when it comes to geosynthetic reinforcement. So what we have here is an HDPE geogrid. That's an extruded geogrid. We've got a welded polyester geogrid, we've got a knitted polyester geogrid, and we've got a woven polyester geogrid. All these geogrids have an ultimate tensile strength of 100 kilonewtons. So the question is, do all these geogrids, even though they have the same tensile strength, will they offer the same level of performance? So this is a challenge facing engineers as they see an increase in the number of geogrids entering the market. So the purpose of this session today is to provide an understanding around the difference between the different reinforcement types available in the market, learn about the properties of these reinforcement materials that are used for reinforced soil design, and then how we go about calculating the long-term design strength of the reinforcement. And as a designer, it's critical to know what properties are relevant for the application. I would like to acknowledge a number of manufacturers, Solmax, Tensile, and McAfee, for some of the content used in this presentation. So the agenda will start off with the applications where these geosynthetic materials are used, talk a bit about soil reinforcement itself. We'll then look at the various polymer types available to manufacturers, the different types of reinforcement that are manufactured. Then we will spend most of the time looking at how we define the allowable design strength of reinforcement. And then we'll run through a very simple example to finish off the session. So there are four main applications where geosynthetic reinforcement is used, starting off with vertical structures. These can be walls and bridge abutments. Then we move into slopes, and these slopes vary from typically 70 degrees down to a 45-degree slope. We then have embankments over soft ground, and that soft ground maybe just the embankment may be laid directly on the soft ground or laid on piles placed into the soft ground, or we may have zones where the embankment is over say, mine workings, where you got potential voids forming. And then lastly, reinforcement used in veneers. So landfill cappings would be an example of where geogrid typically is used to support soil on a liner material. So those are their various applications. So let's look at soil reinforcement. So designs of soil reinforced structures are normally carried out by geotechnical and or structural engineers. So while these designers may be familiar with soil and concrete, often they know very little when it comes to the different polymers available in the market. So intuition and use of default values for soils and concrete is likely to produce safe structures. So that comes with a lot of experience. However, a lack of understanding when it comes to polymer materials and its production into a geosynthetic requires careful evaluation of the material properties. It's not a straightforward exercise and does require a bit of evaluation. And avoiding speculation about long-term geosynthetic properties alleviates designers' concerns and obviously reduces the risk associated with that. So let's look at soil reinforcement principles. Starting off, soil itself, high in compressive strength, but low in tensile strength. So the reinforcement is there to absorb those tensile loads, reducing the loads that would cause shear failure of that soil mass. The soil reinforcement is installed across the active and resistance zone interface, and it's important that that reinforcement has sufficient tensile strength and bond so that it can transfer the load from the soil to the reinforcement in the active zone through to the resistance zone. So most of you would be very familiar with those concepts. And what we have here is an image, and this is used by a lot of presenters of soil reinforcement. So this is a very old structure built somewhere between 500 to 1000 BC. It's a ziggurat in Iraq, and was built out of clay bricks and papyrus for the reinforcement. So one of the earliest reinforced soil structures. That's what it looks like, something along those lines today. So there's still remnants of the structure around, and if you look closely, you'll see the papyrus in there. So one could argue that maybe the engineers of the time over-designed the structure somewhat, a little bit beyond the sort of 100 or 120 year design life. But the concept is well known and has been around for a while. So our focus in soil reinforcement is carrying the load with the reinforcement. The reinforcement bond is a totally separate topic, and we won't be covering that today. We're really focusing on the actual reinforcement design to accommodate the out of balance forces of these different structures. So moving on to the polymers used in the manufacture of different soil reinforcement types. So on the right, you can see a graph just showing your tensile strength on the y-axis and strain on the x-axis. And you can see that these materials differ in terms of their stiffness properties. So starting off with the polyethylene terephthalate, so commonly known as polyester, typically it gets used in soils where your pH is up to about a pH of 10. Anything above that is not really suitable. However, it does have low creep properties. Polypropylene. Polypropylene is very suitable for a wide range of chemicals in soil. However, the creep properties are a lot higher, more susceptible to creep. Same thing with HDPE, once again, extruded polymer, like polypropylene, good chemical resistance, but high creep. And then the more sort of specialist materials, polyvinyl alcohol, good chemical resistance. So it's a bit like the polyester in terms of creep performance. But what you find with this particular material is that it's a lot more expensive than polyester or HDPE. So we don't see too much of PVA in soil reinforcement. And then lastly, the polyaramid fibers. So these are your very specialist things like Kevlar, and which is the DuPont trade name for polyaramids. Very expensive, rarely used in soil reinforcement. Very good tensile, stiffness properties, but very expensive. And I've yet to see in my 30 years it being used in soil reinforcement. So the different types of reinforcement around. So we've got different polymers being used by manufacturers in different reinforcement forms. And the first one that we can look at are the woven geotextiles. So it's a textile-based sheet form. And you'll see most of the different polymers are used in the manufacture of these woven geotextiles. Then there are three subgroups under geogrids. You've got the extruded and drawn sheets. These are typically manufactured from polyethylene or polypropylene. You've got the textile-based. So these are your knitted and woven geogrids from polyester, polyaramids, or polyvinyl alcohol. And then lastly, you've got your welded grids from either polyester or polypropylene. And it's important to note that when it comes to uniaxial geogrids, you'll tend to find that with those, they're either HDPE or polyester primarily. And then lastly, you've got your very specialist geocomposite reinforcements. These materials make use of the good creep properties of, say, polyester, and then they have a sheath or some form of casting of a polyethylene to protect the polymer reinforcement from installation damage and chemical effects. So very specialist products. And here's some images of these different materials. And what you'll find with all of these materials is that they're very efficient in carrying the loads generated in soils. And these materials, these polymers, are quite different to, say, with polyester, the polyester shirt that you wear. It's a very high tenacity type material, or the HDP is drawn. So they develop their strengths at very low strains. They generally have good in-soil durability because of the highly drawn or high tenacity type of polymers being used, and they're very efficient in developing their strength in a very short length. Okay, so that's just given a bit of a background to the different polymers, different soil reinforcement types. Let's now move on to how we go about defining the allowable design strength. And this is sort of the main sort of thrust of the session that we're going through. So what happens when to the reinforcement after they've been purchased? So they arrive on site in pristine condition. So they should, most of them arrive with a wrapping protecting the rolls from weathering effects, UV, etc. Some of the products like HDPE don't require that wrapping. So the material is stored in a suitable location, protected from weather, and made sure that it's not exposed to vehicle traffic that could potentially damage the reinforcement. The material is then installed, and it is subject to installation damage during this installation process. So from the placement of the aggregates and compaction of those aggregates over the reinforcement, and any trafficking that takes place after that. And then as the structure is built, the tensile loads are taken up by the reinforcement at certain strain levels. And then over the life of the structure, that reinforcement is subject to creep in the long term. So that's strain taking place in the reinforcement over time, subject to environmental durability and temperature effects. And we're going to go and discuss each of these specific points in the following slides. So here is the typical formula that we use for determining the long-term design strength. So TAL is tensile allowable. And we start off with the ultimate tensile strength, and that is divided by reduction factors for installation damage, for creep, and for environmental effects. And it's important to note that the extrapolation of data needs to be considered when looking at reduction factors for creep and environmental effects, because when we do our testing, it's not possible or not practical to test for the 100-year design life, for instance, have that level of data. So we're having to use techniques and extrapolate out short-term testing over that period of time. It's important to note as well, and under the environmental reduction factor, that weathering effects comes into play in that area. And in some instances, some manufacturers say that if you expose the reinforcement to a period of greater than, say, 24 hours and up to 2 weeks, you need to add an additional reduction factor to the reinforcement. So it's important to be aware of these particular requirements. Obviously, if it's covered within 24 hours, the reduction factor for weathering is a factor of 1. So the above procedure is consistent with what you see in different parts of the world under different codes of practice. So you've got the British BS 8006, EBGEO, and AS 4678 closer to home, the Australian standard for retaining walls or retaining structures. The actual form of the formula will vary slightly with all the different either partial factors or reduction factors, but in principle, those main areas are all the same. So let's look at the load time framework. So time being on the x-axis from 0 through to the design life of the structure, and on the y-axis the load being applied to the reinforcement. And we're going to use this as the basis for the following slides to try and understand the various properties that need to be considered when determining the allowable design strength. So we start off with the ultimate or initial tensile strength of the reinforcement. There's a standard test method for carrying out this test. It's either the European ISO 10319 or the American ASTM 0.4595. So you're looking at a 200mm wide specimen that's clamped in jaws, and typically for these specialist reinforcements, when you're starting getting up to 1,000 or 2,000 kilonewton per meter product, you need very expensive test equipment to be able to ensure that no slippage occurs in the jaws. The tests are carried out either at 10 or 20 degrees C, and that's very important because there's a difference for some polymers. They're more creep susceptible to temperature. So you'll find that at 10 degrees C for a HDPE, for instance, it'll have a higher strength than at 20 degrees C. So it's an important consideration to take into account, that is temperature. And then you have different strain rates for the test methods, 20% per minute for ISO and 10% for ASTM. So here we have a typical stress strain curve. Typical, it's like S curve that you get for polyester geogrids, and you see that most of these geosynthetic reinforcements will develop their ultimate tensile strength at somewhere less than 12% strain. So it's all very well getting the test values. How do we use those values? And this is where statistics come into play. From an engineering point of view, for engineered structures, we would not consider using average or typical values. We don't want 50% of the reinforcement arriving on site from a manufacturer being below what we're considering in our design. So we always require that the reinforcement is represented as a 95 percentile or characteristic value, or what the Americans use as a MAR value, which is also 95 percentile value, which is typically your mean minus 2 standard deviations. And it's important that when these tests are carried out, they're carried out in an accredited laboratory, i.e. that test equipment has been audited and shown to be acceptable in producing these results. The next area that we're looking at is the installation damage. So this is an immediate loss in strength during the construction process. So we're dropping down from an ultimate to an installed tensile strength. To obtain the reduction factors for installation damage requires full-scale testing where the reinforcement is placed out on a bed. There's different aggregate types placed over it and compacted, and then it's carefully exhumed. And you'll have a pristine sample from that batch, and then you'll have these samples that have been subject to damage that are then tested, and a reduction factor for installation damage is obtained. Now, it's important to note, if you recall earlier on, you can see that the geosynthetic reinforcement comes in all different shapes and sizes, and that has a big effect on installation damage. As you can appreciate, the surface area, the greater the surface area, the greater the contact of the aggregate to the reinforcement, and the greater the likelihood for damage. So, you know, and the same thing with thickness. So the thicker the product, the less the damage is going to influence the strength. So the different shapes and sizes of reinforcement will result in different levels of installation damage. And one can't just estimate this. One has to have proper full-scale testing to determine what those installation damage values are. And typically what you'll tend to find is that the coarser the fill, or especially more bonier fills, you'll get a higher level of installation damage. So it's always good if you're using granular fills to have a well-graded granular fill to manage that installation damage. The more bulkier the reinforcement, the less insulation damage, so it only tends to occur to the outside fibers, and the inside fibers are protected, providing good level of reinforcement. And you'll find in test reports there's typical gradings of the material being used. Typical practice is to test several grades of the product to be able to obtain suitable reduction factors for the full range of products, say from a 40 kilonewton geogrid up to a 200 kilonewton geogrid. Now, installation, as I mentioned, is an immediate effect, whereas the next two factors, factors for creep and for environmental effects, occur over the design life of the structure. So it's important to understand what design life you're considering, whether it's a short-term temporary type structure, say up to about 5 years, or it's a highway structure where you potentially up to 100 to 120 years. In most instances, you'll find that the reinforcement design life needs to be equivalent to the structure design life. However, there are certain instances, such as embankments over soft soils, where the embankment's going to be there for 100 years, but the reinforcement is there just temporary, until such time as the soil in the foundation consolidates and provides sufficient reinforcement as support, and then the reinforcement becomes surplus to requirements. So the reinforcement really has to perform for most of these design lives. Okay, so now sort of getting into more this sort of chemistry or the creep rupture effects when it comes to these polymer materials. So the issue that we face with polymer is that whereas metals, steel is totally crystalline, i.e. it's a solid material, these polymers are manufactured from petroleum oils, which are totally amorphous. So they're shapeless in their form. So these plastics have both crystalline and amorphous regions, and the amount of crystallinity, the amount of polymer of the molecules, the density of these molecules, the bonds between the molecules and any cross-linking that takes place, as well as the glass transition temperature, differ from one polymer to another polymer. They all differ. So for instance, HDPE does not form any cross-linking, resulting in higher creep potential. So we need to understand that each polymer is different in terms of its creep performance. So let's look at how we assess the creep rupture effects. So typically when exposed to stress, a polymer material responds in an instant elastic deformation. And this is reversible, whereas you also get a slow viscous deformation, which is irreversible. And this is what we refer to as our creep. So creep is really a fundamental characteristic of these polymers when carrying loads over time. So that irreversible deformation, this creep, is really the slippage between the various molecular chain segments, which helps relieve stress. A bit like when you have earthquakes and you get the ground moving, and then the stress is relieved as the ground moves. So it's these chain movements that are defined as creep, relating to an increase in the deformation of the reinforcement under that constant load. Now, it's important to note, as I've mentioned already, that the amount of creep is influenced by the polymer type and the structure of the polymer. The more drawn the polymer is, or the higher the molecular weight, all influences that level of creep that takes place. Creep is rate related, and consequently it's governed by time and temperature. So the longer the period of time, the greater the level of creep, and the higher the temperature, the ambient temperature in the soil, the greater the level of creep. For most areas in New Zealand and in Australia, your in-soil temperatures are up to about 20 degrees C, and that's what you would typically work to. But there are some areas, certainly in Australia, where 25 to 30 degrees is appropriate. So I've been saying that there's different creep effects to different polymers, and here's an example where we've got HDPE and polypropylene. So these are actual creep testing on both HDPE and polypropylene. So you've got your HDPE on the left, and on the right the polypropylene. This is courtesy of Tensile International. So what we're going to do is we're going to test to failure. For the HDPE, we're testing at a constant load of 47% of ultimate, and what we find is that after 2 years we get failure of the HDPE. Applying the same constant load for around 47% of the load, what we find for polypropylene is that it fails in 4 days. So a dramatic increase. What are the implications of that? The implications are that if you're designing a structure for HDPE, you'll have 11 layers for a 5-meter high structure, whereas you have 3 times the number of polypropylene geogrids, all having the same tensile strength as the HDPE, but the higher the level of creep. So quite a difference in performance with those different polymers. Now, it's important to note that polymer is elastic, because after strain due to the load, it's capable of recovering. On the other hand, they're also viscous. So they elastic, viscoelastic materials. And it's important to note the glass transition temperatures of the different materials. So what you'll find for polyester is that the glass transition temperature is around 100 degrees C, which is higher than the operating temperature of 20 degrees C that we normally work to. Whereas HDPE is minus 100 degrees. Now, for those of you who are not that familiar with glass transition, it's basically the glassy state of the material, and at that transition zone, it goes from that glassy state to a soft, rubbery state. So essentially, the molecular bonds in that loose state are above the glass transition temperature. What you'll tend to find with the different polymers is that your polyesters, your PVAs, polyvinyl alcohols, and polyaramids are essentially elastic materials because their glass transition temperature is above that normal operating temperature, whereas polypropylenes and HDPEs are viscoelastic. So hence, you'll get more creep occurring in polypropylene HDPE compared to polyester and PVA. So how do we go about testing it? It's all very well having all of that chemistry around, but we actually need to do physical testing. So conventional testing involves 10,000 hours of placing loads on the reinforcement in a controlled laboratory. So this ensures that you have a maximum of 2 log cycles of extrapolation to achieve a 100-year design life. Now, there's also accelerated testing that can be carried out to extend the design curve to more than 100 years. and give greater confidence to that design curve as part of your extrapolation of data. And there are different techniques that are applied. The first technique is the time temperature supposition. And this method is where we test the polymer at different temperatures. These are long-term tests. So these are anywhere from 1,000 to 10,000 hour long tests at 10 degrees, 20 degrees, 30 degrees, and 40 degrees. And as we mentioned, the higher the temperature, the greater the creep. So you're able to time shift the data to get that plot as shown over there, to extend your creep curve to greater than 100 years and have a higher level of confidence when it comes to the actual creep that's going to take place in the reinforcement. Now, that time temperature supposition has been around for a long time. It's not possible to do that with polyesters. There's a different method, and that's the step isothermal method that's applied for polyesters. And there it involves multiple short-term tests at different temperatures on a single sample to do essentially the same thing where you're doing these plots extending beyond your 100-year or 1 million hour target design life. So those are the techniques that manufacturers are able to use to support the creep factors. And, as you can see from the graph, the level of creep varies from polymer to polymer. And what you see in the table are some typical range of values that you will see for different types of polymers. And you'll see that the high modulus polyesters tend to have the lowest level of creep, whereas your polypropylene, woven, so lower modulus woven geotextiles, have a high level of creep. So quite a range in reduction factors. So that's all good for the different polymers. What about the environmental effects? So the second part of our long-term effect on the reinforcement strength. So when it comes to a soil reinforcement, what we tend to find in most engineering soils used in civil construction is that these environments tend to be benign. So having a pH of somewhere between 5 to 9. However, if you start adding cement or lime to treat the soils, that can have a major effect on the pH characteristics, and that may limit you to the type of reinforcement that can be used with those soils. So let's look at what effects there are. And there are two long-term durability considerations that come into play. The first is oxidation, and this applies to polypropylene and HDPE reinforcement. So in the early days, with pipe manufacturers, polyethylene pipe manufacturers, where they didn't make use of stabilizers, very quickly these pipes oxidized, so they got brittle and then they cracked. So we've come a long way from that time, and we now use stabilizers to address the short-term and long-term effects. And most manufacturers have a master batch of different stabilizers that they use for their manufacture of their materials. The polyester and polyaramids are not immune to environmental effects. And one of the sort of downsides of these types of materials is that they are subject to hydrolysis. And the lower the molecular weight, the greater the degree of hydrolysis taking place. So this is when the molecular structure of the polyester is broken down through attack with these high pH materials. So you do require a degree of temperature, you do require high pH, and you do require moisture for hydrolysis to take place. What you'll tend to find, for example, you'll see specifications like in the US that you'll have a molecular weight of greater than 25 grams per mole and a carboxyl N group value of less than 30. So there are specific requirements to limit the level of hydrolysis that can take place in these materials. Anything above a 10, you want to try and avoid using polyester or polyaramid type materials. Of course, environmental reduction factors are needed to be taken into account for the durability. And bear in mind that higher the temperature, the greater the effect on durability. So in some very harsh environments where you've got high temperatures, special care needs to be considered. So let's look at the typical reduction factors. So for most conditions where you've got benign soils, reduction factors for most of these polymer materials are close to 1 over the design life of the structure. Obviously, the rate of degradation increases, as I mentioned, with high temperatures. Most testing is carried out for degradation at 20 degrees C, which is the average soil temperature for our particular region. Bear in mind that anything above a pH of 10, the PVA, HDPE, and polypropylene remain stable, so they're very suited for those applications. One thing to bear in mind in terms of the weathering environmental effects is the covering of the reinforcement. Typical practice, so if you look at the British Standard EN 14475 2006, execution of special geotechnical works, reinforced fill suggested for reinforcing geogrid geotextile. That recommends that the material is covered within 24 hours of exposure. And most manufacturers / suppliers will have guidance in terms of covering the reinforcement. As I mentioned, the rates of degradation for polyester and polyaramid increase at high pH levels. So we've now covered all these factors to be considered when determining the allowable strength, the long-term allowable strength of the reinforcement. We'll now move on to how we apply this in practice. So we'll have a look at an example. So the example that we're going to use is a 10-meter high wraparound structure for a highway works. So it needs a 100-year design life. We're using a coarse, clean sand as a backfill. And there will be some form of facing, in this case, a precast concrete panel facing, and that will protect the reinforcement from any long-term UV or weathering effects to the reinforcement. So what we do is we go about and we start with the design of the structure. So it's an example of designing the structure. And what we find in the design is that the maximum load being applied is, in this case, 41.92 kilonewtons in all the layers. So that's the maximum load being applied. We then go and put out our specification, and we require that the long-term design strength at a temperature, in this case 20 degrees C, for a 100-year design life with a fill material up to 2 millimeters, i.e. a sand, in that pH range, has a strength of 41.92 kilonewtons. And it's up to the manufacturer to supply the data to support their material having meeting or exceeding that particular strength. And no manufacturer is going to match it directly. It should always be above that strength. So we go back to our formula where we've got T allowable equal to the ultimate strength divided by the reduction factors for installation damage, for creep, and for environmental effects. So in this case, I'm going to take one of the data sheets. This is for a product called MirrorGrid, and we are using MirrorGrid GX. And from the technical data sheet from the manufacturer, what we find is we have a reduction factor. And sorry, it's difficult to see there the data, and I didn't get a chance to blow up the different sections, but for installation damage under the MirrorGrid 80, we've got a factor of 1.05 for sand. For the 100-year design life at 20 degrees C, we've got a reduction factor of 1.43 for creep. And then for environmental effects, for, once again, 100-year design life, for that pH range, we've got a reduction factor of 1.05. So we then plug those numbers into the formula, and we get an allowable strength of 50.74 kilonewtons per meter. So that is the safe design load, long-term design load for MirrorGrid, and that should be GX 80, not 100, which is greater than the required 41.92. So we get an acceptable outcome for that product. And that's how one would evaluate the long-term design strength for different reinforcing materials. And it's up to the suppliers to be able to, suppliers/manufacturers, to be able to supply sufficient data to support those factors. And in some places, some of the states in Australia and in New Zealand, for instance, the roading authorities have an approval system for reinforcement, where you can only consider those products that have already been approved for your highway structures. So some concluding remarks. So geosynthetic reinforcements are manufactured with a wide range of tensile strengths and strains. So you'll find that reinforcement starts at around about 20 kilonewtons and can go up to 2,000 kilonewtons per meter. Most of that reinforcement, the strains it develops at ultimate at strains of somewhere below the 12%. Some of the more modern, up-to-date polymers are a little bit stiffer than that, and they're getting their strains down at less than 10%. When you place reinforcement in different compacted fills, they are subject to installation damage. So it's important to pay attention to the selection of the fill to be used. You want to be very careful of some of the sort of cheaper run-of-pit type fills that can be more poorly graded, which would cause a higher level of damage to the reinforcement. So very important, the grading of the fill, the type of fill, and the level of compaction that's applied to that fill. All these geosynthetic reinforcements are subject to creep, different levels of creep for different geosynthetic reinforcement types, and that needs to be considered along with the temperature that the reinforcement is going to be subject to in the soil. When the reinforcement is installed in these different soil conditions over the design life, they're going to be subject to environmental effects, and these need to be considered. especially if you've got wraparound structures, that they need, those wraparound structures do need to be well protected in the front face over the long term. 100 years or 120 years is a long period of time that you have to predict what's going to happen to that reinforcement over that period of time. So careful consideration around that. So understanding all these factors around polymer reinforcement is extremely important when evaluating different products against your project specification. So hopefully this session, this presentation has allowed you to have a better understanding of what you need to be looking for when selecting your saw reinforcement for your reinforced saw walls and slopes and embankments. So I'll now open to any questions. At the moment, there's no questions in the Q&A. But if anyone wants to ask any questions, we'll give it a few minutes to ask any questions. We've got a few minutes left before the hour is up. As I mentioned, a recording of this webinar will be made available on the Academy website. Look, the other point I do want to make when it comes to saw reinforcement is it's important to properly evaluate the manufacturer's data sheets. There's a lot of data sheets out there, and it's important to read the fine print and get clarification around the information. There's, it's got to be consistent, the data out there. The other point I would like to make, and this is more for the New Zealand audience, is that work is currently underway to address the specifications for highway structures by Wakakatahi, the New Zealand Transport Authority. So there's a process underway at the moment where they're looking at trying to get consistency around specifications, because what they want to avoid is where you use a brand name or equivalent, because that opens up a lot of risk to the designer and to the client in terms of the evaluation of the equivalent by that particular designer. Okay, so we've got a question. Well, there's a comment thanking us for the info, and it's only a pleasure. That's what we're there to do, is make everyone aware of what you need to consider when using these materials. Got a question here. Question says, regarding the idea of identifying the allowable tensile strength of select fill and example, I assume it was done using a computer program. The strength of the fill, so when we talk about strength of fill, we're talking about the friction angle and the saw strengths, so friction angle and cohesion of the fill. That's a geotechnical consideration that needs to be input into the design. So it's not a geosynthetic, it's a geotechnical, and that's when it comes to the reinforcement. Yes, you do have to start off with a reinforcement type to get the design to an acceptable level, but you don't necessarily use the reinforcement type in your specification. You use the actual design load that you require, because as soon as you use the reinforcement type, you start getting some confusion around what is equivalent and what is not equivalent. So best practice is to actually use in your specification what the design requires. So hopefully I've answered that question regarding identifying the allowable tensile strength of the select fill in the example. So you do have to start off with a reinforcement type. So we're going on 3 o'clock. There's no other questions. So on behalf of Geofabrics, I'd just like to thank all the participants to today's webinar. As mentioned, recording will be made available, and please feel free to reach out to any of the Geofabrics team in Australia or New Zealand if you have any further questions regarding the various reinforcement types and how we go about determining the long-term design strength. So thanks very much for your time, and I will now close the webinar.